Okay, so welcome to today's Mitake PT reading seminar. So today's speaker is Adrian Calderon, who is a student of UW Madison. So he's gonna talking about large time behavior for a cutoff mean curvature G equation with source. Please.
Thank you for the introduction, and thank you all for coming to this talk. Um, as Professor Mitake said, yeah, I will be talking about large time behavior for this G equation. Uh, So this talk is outlined as follows. I'm going to discuss some motivations for the PDE that I studied, and then as just in case there are some people that are not familiar with the viscosity solution and the framework, I included a small preliminary slide so that we can talk about that, and then I'll discuss the assumptions and the main results. And then I'll get into large time behavior for both settings, the periodic and the radially symmetric setting. And in this talk, I'll mostly focus on the radially symmetric setting and discuss some dynamics with the trajectories for minimizing the cost over trajectories. And then I'll say a few things about local regularity at the end. Okay. So the equation that I study is coming from two sources of two different fields of study. One's with turbulent combustion, which they in the research communities they consider the G equation. And when discussing a flame front, just whenever say a flame is propagating a bit, one part of the boundary is propagating outwards. It's likely to take along neighboring points on the flame front. So this is where the curvature operator kicks in. And then here the cutoff operator is just to prohibit any non-physical burning. So you can think of it as a perhaps in a wildfire. Once the fire has already passed over some dry wood, then the flame won't come back and burn that region again. And then there's also motivation coming from crystal growth, birth and spread models, where the crystal height is represented by the value function, which solves a Hamilton-Jacobi equation. And here the source represents deposition, so maybe dropping crystals in certain parts in the domain. And then here the cutoff could represent the a crystal that lies in a supersaturated solution where dissolution is not preferred by the system. And then here curvature again makes its appearance where usually whenever you're talking about chemical reactions, the surface tension of like the surface of the well, yeah, I guess a service kind of keeps things together, so it's not really discontinuous. And many work's been done in these two fields to show that asymptotic growth speeds or effective burning velocities exist, which is natural to expect. Then large time profiles can uh, be possible. So the PDE that I'm considering today is the cutoff mean curvature G equation that has the source. And just wanted to point out a few things. Here, F is a non-negative source. Again, you can think of it as just depositing new crystals in different parts of the domain. Or if you want to think of it in the flame front view, you can think of it as like replenishing fuel. So perhaps dropping more wood into a certain spot that even though it was already burned, but it can be burned again. W is the wind vector field. So this can be in cases that's been studied by Hung, such as a shear flow that can be represented by the wind vector field. And here it's again the cutoff operator is just defined as the maximum between zero and the argument, so it prohibits any retreat of the front. Well posedness has already been studied, so I'm just studying some finer properties, such as large time behavior and the regularity. Some notable things about this PD. It's non-coercive in the gradient argument, and it's non-convex. In general, as you'll see when I talk about it in the radially symmetric setting, actually becomes a convex Hamilton-Jacobi equation, which will take advantage of the representation formula that comes from that. The non-coercivity will present, as many of you know, when we lose or when we don't have coercivity, usually regularity takes a hit from that. Despite these, the PD is, however, non-negative definite, or at least a nonlinear term, which is very useful in the arguments and allows us to find the Aubrey set easily. So just a small, quick primer on viscosity solutions, just a refresher for those that need it. If you just consider a first order Hamilton-Jacobi equation, here the Hamiltonian is quite general, so it could be nonlinear and definitely doesn't have to be in divergence form. So integration by parts is not a good solution to find some to be able to pass derivatives onto a test function. So we do this by using the maximum principle that we learned back in the day in calculus. And the idea is that if you have so viscosity subsolution is going to be defined as just for now, just think it's a bounded continuous function. And if you can touch it from above with a test function that's smooth at some point, say x naught, then that the function u minus that test function has a maximum at that x naught. And if everything's smooth, then of course the gradient of that function is zero. Hence, the gradients have to match for the for the solution and also for the test function. And then, of course, the Hessian is going to be non-positive definite. So with these, we pass the derivatives on from the potentially not smooth solution to the test function. And so anytime I say solution, I mean it in the viscosity sense. So describing the settings, so we have the periodic and the radially symmetric settings. Here, just the main, I'll just highlight the main things, but here the source is again non-negative, and we define calligraphy A, which is that we call the Aubrey set, is defined to be the set of all points that make our source equal to zero. And we assume that this is contained in the set of all points that make our wind zero. In other words, whenever my source is zero, then that means the wind is also zero. Examples of this you could think of are, well, one, whenever the wind is trivially zero, or whenever it's a constant vector field multiplied by the source function. And then in the radially symmetric case, here we of course impose radial symmetry for the source and the initial data. And then we also will have some sort of uh, um, long range profile for our source, meaning that when r goes to infinity, our source will converge to some constant that's positive. In other words, if you go far enough, you'll eventually there will be a last radius in the Aubrey set. And then in this radial symmetric setting, I just consider the trivial wind vector, and then of course we always assume that the Aubrey set is non-empty. Okay. So here I have the main results, and I'll just state as these are the large time behavior results. So here we have that the viscosity solution to the Cauchy problem converges locally uniformly to a stationary solution. And this is both in the periodic and the radial symmetric case. So strategy for the large time behavior. This is using the half relaxed limits that were first introduced by Guy Guy Barrel and Bertam. And the strategy of using the half relaxed limits to prove the large time convergence is something that was introduced also by actually I'm not sure how to pronounce it, but Nama and Roquejofer. So I think they're one of us French, I think. But so that was a strategy that was introduced by them. And so the idea is that good candidates for the limiting profile would be our half-relaxed limits. So the lim sup in the relaxed sense and also the lim inf in the relaxed sense. And this is a great these are great candidates because in the viscosity solution framework, we have the strength of stability. So here we have that indeed, if U is a viscosity solution to the Cauchy problem, then U plus will be a viscosity subsolution to the stationary problem. And on the other hand, U minus will be the super solution to the stationary problem. And again, we use the property that we can we'll show later, but on the Aubrey set, we actually have that the map that maps time to your solution for any fixed x on the Aubrey set is actually non-increasing. So it's a monotonicity set. And so hence we have that U plus is actually equal to U minus on this Aubrey set. And then lastly, the idea is to apply the comparison principle where we have an ordering on the Aubrey set, and this ordering will be propagated to the rest of the domain. And so this will give us our large time convergence. Right. So here's just the stationary problem rewritten in just in the form. And so here I just wanted to show that just a PD argument as to why we can see the Aubrey set as a monotonicity set. So we just assume for now that X is on the Aubrey set and that we're smooth. Then you have that UT is necessarily less than or equal to zero, as our nonlinear operator is actually non-negative. And so this is just a PD argument, and later we'll see the representation formula and how that, with that perspective, how we also get monotonicity. So the main tool, really where all this large time behavior hinges on is the comparison principle and being able to prove that on the Aubrey set and for the ergodic problem. So here is the statement in the periodic setting. And in this talk I want to focus on the radially symmetric side of it, so I'll actually show the proof in that case, but I will omit this one in this case. But the idea is you'll have I hope you'll see the kind of the ideas and the flavor of the proof in the radially symmetric setting, and it can be applied to this. So the main thing is we use doubling variables method, which I'll describe more in detail in the next setting, and also the one homogeneity of the PDE. Okay, so moving on to the radially symmetric setting, just to recap, of course, we'll impose radial symmetry on the forcing and the initial data, and here we can just reduce the Cauchy problem into the just radial derivative. So here actually reduces down to a much easier equation. Here, the Hamiltonian defined as that is actually convex in P. So by the standard theory of Hamilton-Jacobi equations, we have a representation formula, which is given as you're minimizing some running cost, which the running cost is going to be the Lagrangian of the system, and then plus you have to pay for a entry. Maybe this is like your exit fee for leaving your parking lot where you're at. Um, yeah, and so we're minimizing over all possible trajectories. So in order to study our solution, it's important to understand what the Lagrangian is, and so we can actually compute what the Lagrangian is using the Lagrange transform, which is given above. And since going back to the Hamiltonian, you can see there will be a critical radius, say r equals n minus 1, where dynamics start to shift between once you pass radius n minus 1. You'll see that we're actually the Hamiltonian actually will be coercive, so there's some change in dynamics. So it's natural to decompose the domain into 0 to n minus 1 and n minus 1 to infinity. From any trajectory that is living in 0 to n minus 1, we can compute the Lagrangian, and it's as follows. So it's going to be finite and equal to the forcing to the f function, the source term, whenever our velocity is bounded between these two quantities. So we have to satisfy some sort of speed limit here. And whenever our trajectory lives in n minus 1 to infinity, it's also will be finite as long as its velocity is in this satisfies the speed limit. So just combining these two, we have that the admissible trajectories can just be described as this speed limit right here. And just for simplicity, we just define this class as with that calligraphy C. Just some dynamics, just so you can see it geometrically. Whenever our trajectories cross into the region 0 to n minus 1, essentially we're doomed to decrease. So either maybe you can stay constant, but eventually you're going to be decreasing down to your terminal point R star. Um, but as you can see, kind of like at the n minus 1 radius, you can see like so I dotted, but trajectories can cross over, but on the other side of n minus 1, perhaps you can't really say for sure what the trajectory would look like. It can go left or right in the region n minus 1 to infinity. So if we have some terminal point r star, then we can exclude automatically a lot of trajectories as long as they begin outside of this cone of influence. Because if it starts outside of this cone of influence, then in order to reach r star in the finite time t, it had to violate one of the speed limits. So we can just kind of refine our representation formula as follows, and this will be kind of useful whenever we're using it. Nicer and cleaner to look at whenever we're doing some proofs. Okay, so just like we did showed that the Aubrey set was a monotonicity set in the periodic setting, we can also do this in the radial setting. Here, instead of using a PD argument, we use more of a optimal control argument, which I hope will show you that the convexity is really nice because it allows you to have two different points of views to tackle certain problems. So it's nice having two hammers instead of one. So I want to show that the value function at r star in T2 is less than or equal to the value function at r star T1. Here T1 is less than or equal to T2. And so the idea is that we just use a suboptimal policy of instead of reaching r star in time T2, I'm going to just take any trajectory that gets me there in time T1 and then just wait. And here, so that's the first integral you can see. And then when we're waiting, we actually don't have to pay any costs since r star it lives on the Aubrey set. And here, that means our source is equal to 0, so we don't incur any cost. And so now we can just minimize over all those possible trajectories that do such a getting to r star in T1 time, and that's of course equal to our value function at r star T1. So here we can get easily that we have its monotone and hence u plus equals u minus on the Aubrey set. So here I'm stating the comparison principle in the radial setting. And here we'll use, since this is an unbounded domain, we're going to make use of the equal linear growths of the subsolutions and supersolutions. And then and show that we can prove the comparison principle with that. Just like we did, and just how I decompose the domain 0 to infinity into two regions. It's we'll kind of be doing that again, but also looking at some important radii. This way, I can divide and conquer and prove the comparison principle on certain subintervals, and then combine all those, and then get it for the whole entire domain. So for example, proving the comparison principle on any possible intervals that look like A, B, where A and B lie on the Aubrey set and the interval within does not. So this would if S1 and R naught are not equal to n minus 1, so if there's some like positive distance between S1 and R naught, then that would cover that interval. And then we'd like to prove the comparison principle on R1 to infinity. So this is the unbounded domain. And then lastly, prove the comparison principle on 0 to S naught. And then once we have those three, we can just, that will cover all possible situations. Right. So this proof uses the famous doubling variables method, and so this is I think a perfect proof or type of proof that where like if this is your first time seeing it, then seeing like how how strong it is, but also how like perfect it is for this type of theory for viscosity solutions. So this is step one. So just assume for now that there's an interval AB where the boundary points lie on the Albry set, and then by hypothesis we just assume that the subsolution is less than or equal to our supersolution on the boundary points. And then this is a proof by contradiction, so we assume that the maximum of V minus W is strictly positive. So there's at least one C in the inside the interval that makes it positive. And then here we're going to use some epsilon room of space of epsilon room epsilon. Terence Tao has that saying where like you need an epsilon room in your argument. This is kind of what we're doing with the scaling with lambda strictly greater than one. And in fact, I'll later after the proof, I'll talk about kind of the intuition behind why we have lambda strictly greater than one and why it's useful in this proof. But yeah, so we're going to apply the doubling variables method. So instead of just looking at the maximizers of v minus w, um, we double the variables. And in this way, you kind of can think of it as like I'm on one single path, and doubling the variables means I just break off the path into two paths. But at the end of the day, we kind of want to go back to the single variable because that's what the original setting was. So we need to make sure that our R and S don't go too far away from each other. And that's the reason for the penalty term that you see in the auxiliary function. As if epsilon is very, very, very small, then this term, if R and S are not very close to each other or like not equal to each other, then this term can be very negative. And here we can show that this auxiliary function, that the supremum or the maximizer actually is strictly positive. So this penalty term will really force R and S to be very close to each other, and especially in the limit. So here we take this sequence of maximizers. We call them R epsilon and S epsilon. And we can extract this, since we're in the compact setting, we can extract a convergent subsequence. So R epsilon can converge to some R hat, and S epsilon converges to some S hat. And since we have our penalty term, we can show that as epsilon goes to zero, that definitely R hat and S hat have to be equal to each other. Okay. And then one of the key ideas for this doubling variables method and why it works with viscosity solutions is this next idea. So if we freeze one of the variables, so say we freeze S to be S epsilon, then we look at the map R mapping to V of R minus that penalty term with S frozen, then we know that this map has a maximum at R epsilon, which if you go back to our definition of viscosity subsolution, this is exactly that penalty term touching V of R from above at R epsilon. So this is a perfect setting for applying the viscosity subsolution test, which when we do that, we get the inequality 5.1. So just plug in anywhere you see the gradient of V in the original PD, just replace it with the gradient of our test function, phi of R. And so likewise, we can do it with the other variable. So freeze R, set it equal to R epsilon. And then again, the map S to W lambda as minus the minus penalty term will have a minimum. And this is equivalent to saying that W lambda is, or the test function is touching W lambda from below at S epsilon. And so we apply the viscosity supersolution test. And on top of this, we use the one homogeneity of the PDE or geometric property of the PDE. So since W was a super solution to the original PDE, then W lambda, which is just lambda scaling of W, will be a super solution, but with a lambda scaling on the source term. And so now we can just combine. We have these Hamiltonians. We have a lot of compatible terms in the Hamiltonian. And so just subtracting, we'll be able to see some cancellation. Um, the Yeah, okay. So I'll just say for clarity, we denote p epsilon to be the gradient of that test function. And so we have 5.3 once we combine both inequalities. Now, the idea is here is that we need to kind of derive some contradiction. From here, maybe if we recall what happens to R epsilon and S epsilon as we send epsilon up to that convergent subsequence, what happens to those quantities? Well, that converges to R hat. And so the right-hand side will those source terms will actually be evaluated at the same point. And so we'll have 1 minus lambda times that source. So this kind of indicates that if we're going to try deriving a contradiction, then the left-hand side should try being non-negative, as you can we can see in the next page. So let me just denote for simplicity that the left-hand side is denoted as A minus B. And so we just break it up into cases. Again, divide and conquer. So whenever B is equal to 0, meaning the argument was actually negative inside the cutoff operator, then we just easily just use the estimate that A is just non-negative. So hence that's done. But whenever B is positive, then we should make use of the degenerate ellipticity or the properness of the operator to get our non-negativity. Um, so here we see some cancellation, and this is because when we go back to here, you can see the test function phi of r. If you just, I wrote phi of r, but if you just think s is not frozen yet, and so think of it as like phi of r of s, where this is the r minus s squared over epsilon. Note that the gradient with respect to r is equal to negative of the gradient with respect to s. So we have some like anti or some equal to equal but with a negative on it. And so this works perfectly whenever we do like this subsolution test and super solution test so that we get cancellation. And then of course we get that this turns in just by manipulation. You can see that this is a non-negative quantity. Um, and then of course we have that 0 is less than or equal to the right-hand side, and then we just send epsilon to 0 up to that convergent subsequence, and we get and use the continuity of f. Then this is going to be strictly negative. One, because lambda is strictly greater than 1, and r hat does not live on the Aubrey set, so f is strictly positive. And then hence we have our contradiction. So, proof of step two. So this is the case whenever we're considering R1 to infinity. So this is the unbounded domain, unbounded interval, and so we are really focusing on the maximizers of the auxiliary function. And so to guarantee that a maximizer will exist, we kind of want to get this into a compact set. And so the idea is to use the equilinear growth of the subsolution and supersolution. And so if you recall the definition of our, so we're using the same auxiliary function. So recall the definition right here. So if they're, grow at the same linear growth, you have V minus, and remember W lambda is lambda times W. So eventually, it's gonna grow. They're gonna have grow faster, and then with the penalty term, it's gonna make sure that the maximizer are always gonna be on between here. Let me see. Yeah, so between R1 and some R infinity. That's for some R infinity really large. And yeah, so this is the kind of the argument, and we can say that the supremum of the auxiliary function on the whole interval is actually going to be attained on R1 to R infinity. And so now we kind of reduced it back to the setting of step one. And then here we can just, since we're using the same auxiliary function, the same subsolution and supersolution test will follow and have the same result. In the region from 0 to S naught, here we have to deal with the fact that we have a singularity at the origin. And the way we deal with this singularity is we want our maximizers to stay away, so we penalize being close to the origin. For any positive delta, it'll be small, but for any positive delta, if R or S is very close to the origin, then this term will become very negative. And we can show that for delta very, very small, we can show that the maximizer of this new auxiliary function is strictly positive. Hence there's going to be some positive distance away between our maximizers, R epsilon, S epsilon, and the origin. And then here, so now we can get some lower bounds on our maximizers, R epsilon, S epsilon, and we'll be in the kind of in the similar setting with step one. But now we have the added, I guess, bonus that our auxiliary function looks a bit has another term in it. So when you compute the gradient of the test function, you just have extra terms popping up with delta. And so, but as you send epsilon to zero up to that convergent subsequence, and then sending delta to zero afterwards, you yield the same contradiction. So combining these steps, so one, two, and three, then we have that V has to be less than or equal to W on all of the half real line. And then we have the comparison principle, and then we apply it to the half relaxed limits, and then this gives us the large time result in the radially symmetric setting. So here's
Adrian,
another representation formula. Uh,
Adrian,
you gonna say something?
you
Yeah.
have not explained clearly the scaling argument and all this. You should explain it
Okay.
for the audience.
Yeah, yeah, thank you for reminding me. Yeah, so why the scaling argument? Why multiply our super solution by lambda strictly greater than one? And why would that, and I guess intuitively, why would that mean that we have that ordering that like V is less than or equal to W? Um, so perhaps we can think of it as so if we go back to our right here. So U is the solution right to the Cauchy problem, and it's basically minimizing some running cost. Um, for now, just think of like, okay, so W looks something like this, but it's a running cost. Either way, it's trying to minimize some running cost, where the cost is given by our source term F. When you multiply, when you consider W lambda or the lambda scaling of the super solution, what is that doing to this running cost? It's on points that live on the Aubrey set. It's not actually changing anything, so it's still you still pay no price when you live on the Aubrey set. But when you're off the Aubrey set, your cost is now lambda times F. So you can think that like as so which lambda is strictly greater than one, so you're incurring a higher cost for any trajectory that you take away from the Aubrey set. Whereas the subsolution, they're still paying the normal cost of f off the Aubrey set, so that's kind of maybe a reason, the intuitive way of thinking why v will be less than or equal to the w lambda. And then just wanting to say something about the representation formula for the limiting profile. Just one, how to kind of like interpret this. So we had the representation formula for the Cauchy problem, and this is the one for the limiting solution. So you can kind of think of this as so say I'm wanting to I'm there's some terminal point that I'm wanting to reach. So say call it R, and I'm trying to minimize my trip of getting there. So you could think of, and the main important thing is that on Aubrey sets, I pay no cost. So maybe it's like I'm on a free tollway. I don't have to pay anything to drive on it. So you can think of this trip split up into two steps. One would be minimizing like finding the most efficient trip to go from any starting point in the domain to the nearest or closest point on the Aubrey set, because this is the limiting profile, so t is going to infinity. Our trip is taking an incredibly long time, and so we really need to be on the Aubrey set as fast as possible so that we incur no cost. Um, and so we stay there as long as possible, and then move on to get to the terminal point R. So the idea is kind of like you're um, not leapfrogging, but like you travel from anywhere, go to the Aubrey set as soon as you can, and then from the Aubrey set to the terminal point, you want to minimize find the most efficient trip to go from the Aubrey set to your terminal point. Yeah. And so I'll say a few things about the local regularity of the solutions. And I just say this to provide two different perspectives of using one PD arguments and then another using some optimal control arguments using the representation formula. I think this is perhaps an interesting thing for those for seeing this. Um, right. So invariance is the main idea, at least in the periodic setting. So our PDE is invariant under translations or spatial translations or time translations. In other words, if I know that U is a, viscosity solution at point X and T, then I know that it will be a viscosity solution at point X minus Y. And so here we can build barriers, which is the name of the game for a lot of these arguments, in a clever way since we have a monotone term, UT. And so by cleverly constructing these barriers, we can show that basically we want to be able to sandwich our solution in between a subsolution and a super solution, and then use the comparison principle to get estimates on the solution. So here we just choose C0 and C1 to be greater than or equal to the Lipschitz constants of the initial data and the source. And then here we can verify quite easily that indeed phi is a viscosity subsolution and psi is a viscosity supersolution. Um, uh, just for completeness, we can show this just by plugging in the initial point T0 and then just using the fact that U is a viscosity solution, and so we get our initial data G of X minus Y. And then play the game of adding and subtracting what you want to show up, and then using that G as Lipschitz, and then we can, because of our choice of C1, we have that this is necessarily less than or equal to G of X. And then likewise, plugging in this barrier into the PDE, the we'll see that this term, this one with the PD with u of x minus y will pop out because it's the only thing that depends on x. And then the extra term, I don't think my mouse is, maybe you can see my mouse, but this term will come out because of the linear term in time. And then again, add and subtract, and then use Lipschitz regularity of the source, and then we have that this is less than or equal to f. So you play the same game with this with psi, and then you get that by the comparison principle, phi is less than or equal to u, which is less than or equal to psi, and then this gives us our Lipschitz estimate. Of course, this could only be true for any finite time t, big T that you give me. Um, and then, of course, as t goes to infinity, this estimate becomes immaterial. For Lipschitz regularity in time, it'll be done in a similar fashion. Use your invariance with respect to time. We can build our barrier functions in a similar way, and then show that it's Lipschitz regular at time 0, and then shift, and then show that our estimate at time s is going to depend on the estimate on time 0. So those were PD arguments, and then I just want to show the representation formulas argument. So here we're just showing that it's also Lipschitz regular in time, and so here we just use that same suboptimal policy that we used before. So I just get to this place in time t1, and then just wait at that terminal point until t2. So here, we're not living on the Aubrey set, so of course we are paying some price, but that price is it's controllable, it's bounded, so it will give us something that we can actually use. And so here we just compare the value function at T2 and then subtract it with the value function at T1, and we have our estimate here. And so this will actually be uniform in R, and this holds for all T1, T2. And then just using, I mentioned before, talking about the properties of the Hamiltonian in the radially symmetric setting. I mentioned that there's a critical radius. So once you pass n minus 1, we get to the good region where we do have coercivity. And you can see as follows. Because alpha is strictly greater than n minus 1, then we have that this Hamiltonian is actually coercive in P. And so using the fact that we already have Lipschitz regularity in time, we can get the for boundedness for the UR. And then so the fact that this bound really does blow up as alpha goes to n-1 just really highlights like the need for coercivity and why the dynamics at that critical radius kind of create problems for the PD. And then lastly, I just want to give some remarks and some open questions, and some perhaps some future work that I'm considering, but just something that I think is interesting for the audience. So we talked about the qualitative convergence to some stationary profile. And then, of course, a natural question you can ask me is, well, how fast does it converge? Do we have some rate for it? And this is obviously, I think, an important open question, but I I think it's quite difficult, and so I think we'll leave it for the the other experts. And then, of course, we just talked about regularity, and so we only have local regularity, and this is likely due to we don't have coercivity everywhere. So this doesn't necessarily give us a hope for the global estimates. Something that I'm thinking about is trying to come up with counterexamples, which I think would be really interesting to see. And then for the cell slash stationary problem, how does what is how does like the vanishing viscosity select the physical solution? So if you just look at the stationary problem at in the radial asymmetric setting, I'd just be adding a epsilon URR to it, and then seeing what happens as epsilon goes to zero. Which solution does it select? I think that's interesting. And then perhaps considering what happens if our force or source term F depends also on the solution. And this could be so maybe in the sense of in the crystal growth setting, you could think of it as like maybe if there's a lot of crystal here in this region, then the scientist will take away take away some of the crystal, or maybe do something to mess with the I guess the crystal there, and so that could be the source term. And then there, what would the Aubrey slash monotonicity set look like? So that would be interesting to describe what the Aubrey set would be. And then, so this work was supported in part by the RTG at the UW-Madison. And then I just want to thank Professor Hung and Professor Matake for their comments and their suggestions whenever I talked about this paper with them. So I would like to thank them.
Okay, so thank you.
Thank you. Maybe also you have a little bit of time. You should also show the audience the literature and explain a little bit where all this model came from, and then we come to questions. Yeah.
Yeah. Yes. So going to if you look in the top reference there, the bifurcation of homogenization and non-homogenization. Um, so in this paper, they discuss the mean curvature cutoff G equation. Here, you can the W is a shear flow, so it's just like you can just think of it like a pool and a wind just blowing on the top. And here they show that so for certain flow intensities, we do have that the effective burning velocity exists. But if your flow becomes way too much, so say like the wind is just blowing an incredible amount, then in fact the effective burning velocity ceases to exist, and so this means that so on the homogenization part of that problem, you lose homogenization whenever you don't have they coincide with the loss of the effective burning velocity. So that was a major motivation for this problem, and so. and with the where I put in the source term, that comes from the crystal growth. So they prove with the source term being of compact support that they can show that the crystal growth has some asymptotic speed. And so with these two papers, it kind of gives them good insight as to like, okay, the large time behavior could exist, should exist, and so that's the main motivations for the structure of the PD. Um,
Yeah,
and yeah,
I see.
like the things that I just
Yeah.
mentioned, they come from the birth and spread type models from Giga, Mitake, and Otsuka and Tran.
Okay, so I have two questions.
Mhm.
Uh, so first of all, about assumption P2, which is a kind of structure condition. So the zero level set of your source term is included
Mhm.
by yeah, W equals zero, right? I
Yeah.
think this is yeah. I know it's very important to get monotonicity and also a uniqueness set.
Mhm.
But have you tried to, you know, I think in general case it's very hard, but have you tried to extend a little bit about this condition P2? Okay, this is the first question. And second
Mhm.
question is about about the asymptotic profile. So I am always interested in asymptotic profile for large time behavior, and radial case you down. Okay, but the
Mhm.
non radial case, this is also very hard question. In general case, it's very hard to answer. But maybe you can find some example which is non-trivial, and by using game theory, you can somehow obtain the lifetime profile. So
Mhm.
it means how the limit equation depends on U0. Maybe W must be equal zero, and F is some very specific one for your purpose. That
Mhm.
yeah. So this is yeah, two question or suggestion.
Mhm. Yeah, thank you for those very interesting questions.
Mhm.
Yeah. Um, yeah, that's something I'll definitely look into. Yeah.
Yeah, and can you sort of explain or at least answer partly Professor Hero question? The first question, I mean, the second one is kind
Oh,
of more like
yeah.
suggestion. Yeah, but
Yeah.
Yeah, for the structure. Yeah, so maybe this is just more for so initially I did the work with just the source term, and then yeah,
Mhm.
you're right. More for structure. It's if I have that this set is contained in the zero level set of the wind vector
Mhm.
field, then I can still use it still gives me the same monotonicity.
Right.
Yeah,
Right.
so I think it would be
You can
interesting to
also
consider.
can you also give some kind of interpretation from your model point of view?
For a reason why the vector field would depend on the source. Yeah.
no. I mean,
No, no.
you
P2.
should explain why P2 is natural. That was his point.
Mm. Um,
Or at not why it's natural, but I mean, in terms of modeling, what does that mean, right?
Yeah,
Like, can
right.
you? Yeah,
That is
this
nice.
is why
Yeah.
also I suggested you to draw a
mm,
picture. That's easier, but
mm.
there's no. Or at least can you draw a front here and explain a bit for the people in the audience?
Yeah, let me find a clear page. Uh, maybe the thank you page. Okay. So maybe this is the front. Um, Here, so the case where the wind vector field is going to be zero, let's just say, let's see. So this is, oh my, yeah. Sorry, this is with my mouse and keyboard. It's gonna be really bad, but okay, I'm not gonna write that. Okay, so yeah. So in the model, what would it mean for? So when my source term is zero, then the wind is zero. Trying to think. Um, so perhaps that would be like perhaps like so whenever f is zero, then means that that we're just letting the flame kind of propagate as normal. So when f the source is zero, then the way it would propagate would be so maybe I should draw some little finger right here. So maybe that's a flame. This has a lot of positive curvature. And if you remember the local laminar flow speed is given by 1 minus the mean curvature. Yeah, sorry, I wish I could be faster. And then the cutoff on that. So you'll see in these terms, then no motion will be done. And this part of the flame front, it will stay here, and these parts will catch up. Let me try drawing like that. So that's whenever our source is equal to zero. So whenever source is strictly positive, then we are removing or moving the maybe we're pushing this back. Maybe we say that here F was positive, so that means our flame front will have to retreat. Not because of the dynamics of the like the of the fight between the constant driving force, which is one, and the fight against the curvature, but because uh, we as the or the whatever is controlling the source is making it positive. So maybe the front has to retreat. So maybe this is like I don't know why someone would do this, but throw fire, throw more wood into the fire, and so the flame probably stops because the wood is cold, but it is fuel, so we can actually burn it again. Um, and then why the wind could be zero here. Maybe in the model, you can think it's like whenever you're adding fuel to a spot, then maybe, maybe you're kind of closing off that area from wind so it doesn't get effects of it. That's something I would have to think about a bit more, and I think
Yeah,
it's
yeah. That kind of explanation is good enough to me, but somehow I think it's better to prepare some excuse for your uh, condition.
mm,
And
Yeah,
yeah,
or at
yeah,
least you can say that, right? I mean, like as earlier, right? I mean, like what you explained from the model that we did with Professor Yifeng Yu, Yaxin, and
mm,
Konamuni. Then we didn't have that vector field, right? You added it because you can consider it, and then at least in your case, you can
mm,
say that when f is zero, meaning that you are not adding any source, right? So at that
mm,
mhm,
at those places you don't have any wind, so there's
wind.
no
Mhm,
contribution from the outside. So those
mhm.
places are isolated in a way
Right.
that you are not putting more fuel, not putting more resource to those places.
mm,
That's why you have the monotonicity, right? Right, and then also, like for example, besides those, right, Jiung he also did some work on homogenizations and others. So I do believe that that can you go to your list of questions? Maybe just one comment that uh,
no. Oh, really? Sorry.
yeah, that's okay. I think that I think that there should be examples for your models and also for the previous results that we did, right? In general, there should be lots of examples in which that your Lipschitz bound is gonna blow up as time goes to infinity, right? I
Mm,
mean, this is kind of already observed in certain regimes. So it should be plausible.
Mm.
Yeah.
Okay, is there any question, comment?
Hi, Adrian. I just have a question on P2. Just can you think of some counter examples of P2?
Some counterexample, yeah, to see if it's
Like,
uh,
if mean vector field is constant and
mhm.
or just a radially like rotational vector field.
Yeah, so if W say is constant vector field, then yeah, I think would have less control over what would be complicated immediately would be finding the Aubrey set. Um, because yeah, if it's a constant vector field, of course some portions of the flame front the direction is or the normal vector is aligned with it, so you have some non-negativity. Um, so at least
Can
yeah,
you
it would
go to the
definitely
PD for people to see, Adrian? Can you go to the
yes.
PD? Yeah.
Yeah, so if it were some constant vector field with some direction, um, only the parts of the flame front where the normal vector is in that direction would be non-negative, and then maybe you could say, or perhaps the other direction, I think, so that you when you move it to the other side, you have some non-negativity. Um, but that's my initial thoughts about it. For sure, the Aubrey set would change and it'd become, I think, interesting thing to look at.
Okay, let's save it for informal discussion
Mm.
because Hero has to go for Giga seminar. So.
Right. Okay, anyways, yeah, I need to go now. So,
All right.
yeah, thanks.
Thank you.
And
Thank you, Hiro.
bye.